Hello, everyone. My name is Christopher Wade, and today, yes, we're indeed going to be talking about physical attacks against smartphones. So the crux of this talk is that modern smartphones employ a high number of very strong security measures in order to protect the boot flow, the high-level OS, and everything around it. Obviously, these can still be compromised, but you're largely seeing very complex attacks to bypass these protections rather than simple, straight, instantaneous exploits. For this talk, I wanted to find two exploits that were very simple and easy to exploit and fun that would compromise the physical security of two of my own phones and see what happened. So there can be two case studies. The first is going to be gaining root access to a smartphone where all of the bootloader unlocking had been disabled. So the standard method for getting root had been disabled. And then the second is going to be a full secure boot bypass on a modern Samsung phone. So rooting on a locked bootloader. Essentially, I had my old smartphone and wanted to root it so I could test mobile applications on it and see what the hardware was doing. On most devices, this indeed has a standard approach, which is bootloader unlocking. You reboot to fastboot, say fastboot OEM unlock, and then the device will reboot and allow you to modify the firmware as you want to. While some OEMs do place restrictions on the list, like requiring their own special applications to connect to the phone to do this, the phone itself had disabled it completely, so you could never boot into that mode, and the attack service of the USB on the secondary bootloader was just gone. The target device was a smartphone from a Chinese OEM released in 2019 and used an OEM-developed fork of Android, which has its own system services and additional security protections to try and harden it more than the standard Android approach. The disabled bootloader unlock actually used a special engineering app that you could only get via contacting the manufacturer or some other means that would store a special signature within a hidden partition on the device, which was inaccessible to other applications and standard users, and would also require you to log in and provide some personal information, which are lots of different steps I didn't particularly want to do on this. So when bootloader unlocking in this manner isn't available, but you still want to get root access, you'll have to use an exploit like you would on a standard compromise of a smart device. With no direct access to the bootloader USB interface, which is the greatest attack vector for when you're trying to escalate privileges on the physical hardware of the phone, I decided to find a vulnerability in the Android fork that had been developed for this phone. The Android fork itself contained a huge number of additional services at the system and root level to facilitate different hardware components that had been added, as well as other security features that had been added. And I was fairly sure I'd be able to find a compromise in one of those that would allow me to escalate to root on the device. So the Android fork had a service running as root, which was called by system-level applications for the purpose of archiving and backing up application data so it can be transferred to other phones for backup purposes and also up to the cloud. This would require higher privileges than a standard application would because it needs to go into the app data of individual applications which are partitioned off from each other on the Android ecosystem. A brief analysis of the binary after I pulled it out of an OTA update image found an immediate command injection vulnerability in the file names of files within the application. So when you would, a service call would be made to this service, if it was a service call which contained the file name with backticks in it, you could actually execute shell commands as root. Unfortunately, SE Linux was in place on the Android device, as it is on almost all Android devices. This can be used to prevent a process with root access from accessing other code portions of the system and keeping it in the context that's been provided. So this root command injection vulnerability allowed me to have access to all the application data on the device, but literally nothing else, and it was very strongly in place. Because it was configured so well throughout the OS, I decided that this was a dead end and that I would try to avoid the HLOS as much as possible. Because the bootloader was out of the question and the high-level OS was out of the question, I decided to go for the next available target, recovery mode. So on Android devices, if you hold down a volume button and power it on, you can usually get into the recovery mode, which is for rolling back OTA update images or factory resetting the device and that sort of thing. It's usually a very standard basic set of options, which are controlled using volume up and volume down buttons, as well as the power key to select them. However, the custom Android operating system that had been added to the device had actually expanded this to have access to the touchscreen, access to the Wi-Fi card, and access to all the storage on SD cards for the purposes of expanding the functionality and making it look a bit better than the standard Android one. In order to find a vulnerability in this recovery mode, however, a firmware image would be really useful, so an OTA update image. I downloaded every OTA update image for the target phone I was looking at and found that none of them contained a recovery image whatsoever. So I wouldn't be able to reverse engineer anything from this device, or from the recovery mode rather, because there was nothing available for me to look at directly, and I couldn't dump it off the phone because I didn't have the privileged access. With no recovery image to reverse engineer, I decided to go for very basic attacks and see if I could replicate what I did on the high-level OS. I saw that it had an option to install from storage or from SD card or from USB OTG an encrypted update. And the OEM had added encryption on top of the standard OTA update format for Android, which I thought would be the most easy to exploit if possible because I'd already found command injection in the high-level OS. So as I'd found it before in a file name, I decided to instantly try another command injection on a file name and took a legitimate OTA update image and renamed it backtick sleep 30,000 backtick.zip, and then tried to load it from the file system. What this did is make the phone sit there all day trying to perform the update, meaning that it would hit a command injection somewhere within the binary, and it would just sat there sleeping the entire time. I disclosed both of these command injection vulnerabilities at this point because they're both kind of basic but quite high risk, but they were very swiftly remediated by the OEM, and new versions of the software were released very quickly. But as I now had command injection at root level in recovery mode, I thought I'd be able to use that to escalate further into the device and gain more privileged access. So first I started with some root cause analysis. Because I had root access into the recovery mode, I could then re-enable ADB and things like that, which we'll be going on to in a second. But what I did to do this was see where in the binary for the recovery binary this was occurring. And what I actually found was that when it goes through the update process, it takes a SHA-1 sum of the OTA update image that's being used, just using the standard exec command to do this. And they had sprintf'd the name of the file name directly into the command, meaning that there was no escaping whatsoever, so a very basic, easy command injection vulnerability. As there was this command injection vulnerability, I could probably use this to execute a more complex script if I adapted the file name a bit more. So by altering the name to include a base64 encoded string, and then decoding that and running it through SH as a very long file name, I could probably use this to load a script from the file system and do things like enable USB, enable ADB, that sort of thing, which is my plan. Unfortunately, the file system used by Android's user data, which is where these files were stored, does not support all special characters. So things like pipes were not allowed by the file system. Luckily for me, another update the OEM had added was allowing ext4 file systems to be mounted to load the update images from. So I took a micro SD card, formatted it to ext4, and added my command injection file name directly into the device. What I wanted to do was gather more information about how much access I now had to the device through recovery mode. I was assuming that SE Linux would still be there because it was on the Android side, but it was also possible that because the recovery binary drives everything within recovery mode, it would have high enough privileges for me to disable it if I wanted to, which turned out to be correct. So what I did was first I run the ID command into a file so that I could see if I was running as root or not, which was very important, and then disable SE Linux with the set enforce 0 command, and then check it wasn't enforcing anymore, and then enable ADB on the device, giving me full root shells into the device via USB in recovery mode, which was very powerful. Now, having root access into recovery mode is quite exciting if you want to poke around what the device is doing, but you're now not attacking an Android device, you're attacking the recovery mode. So what I wanted to do is find a way for me to laterally move from recovery to Android without rebooting the device or touching boot in any way. So essentially switching from one user space to another without bypassing all the setup of disabling SE Linux I'd done. The first option would have been to use kexec, which is a standard module on Linux devices, which allows you to load in a new kernel and execute it from user space. You send it the kernel file, and then it will basically start it from the instance you're in without ever rebooting or anything like that. Unfortunately, the phone itself did not have this module enabled because it wouldn't. That's a security risk to have it there. And so I tried to load it as a custom-built kernel module, but sadly that didn't function because they'd added signature protection to their kernel modules, which was the right idea. So I decided to go for a user space only approach, which is using ptrace. Now, ptrace is a system call that allows another process, a process to call into another process, looking at its memory, debugging it, pausing it, rolling it back if it needs to, and things like that. Typically, this is used for debugging purposes and for certain other tracing, things like using the strace command. However, it's extremely useful for exploitation and modifying running processes as well. Even dep-enabled memory can still be modified if needed. What I wanted to do using ptrace was hook into the init process of Android, which is the first process that runs, and modify it and poke into it to switch into Android from recovery. Ptrace can be configured to immediately pause the process, and then you can modify the subsequent operations to run commands. And if I use the execve command, I could essentially swap out what init was with a whole new process by itself without affecting the device whatsoever. So the commands here are just a few lines of assembly, which essentially load in a execve command, and then performs the service call for a service call at xve. Switch root is used to switch to a new file system on boot on standard Android and Linux devices. You switch from usually an init ramfs and then switch it to a standard higher level mounted one that's mounted by the init ramfs. What I wanted to do was use this functionality to switch root again from the init ramfs of recovery to the init ramfs of Android and then allow Android to boot, essentially switching from init ramfs to init ramfs to the Android operating system rather than what usually happens, which is loading in at ramfs and then going straight to Android. And what my plan was to essentially take the init process, which is usually init, and then init setup SE Linux, and then init second stage, and then inject into it and switch root into Android's init and execute that instead, restarting everything, restarting all the services so that we could restart the whole process without ever rebooting the device. There are a few caveats to this, however, because it was not something that's intended to be done on an Android device at any point. So the first one was an issue with shared mounts. So when you boot up an Android and Linux device, it sets up /dev, /proc, /sys. And in this instance, they'd be set up as shared mounts, which means that they will stay in the same place as the file system moves around. Unfortunately, because I needed to jump into a new file system, I couldn't keep them shared. I needed them to move to the new location. And I could force this by just dumping proc1 mount info, grepping for all the shared mounts, and then removing the shared and making them private, which means they could be moved around as needed. I then needed to patch out all the SE Linux checks. So during the init process, init will check if the proc command line, which is from the kernel, is wanting the device to be booting in an SE Linux enforcing mode. If it does, if it is disabled when this happens, it forcibly re-enables it and makes sure all the SE Linux contexts are set up, which in my case causes the phone to hang and me to have to do a forced restart because nothing about what I was doing was anywhere near what the SE Linux configuration was doing. What I did was take ptrace again, override all system calls for file reads, and if it was reading from the proc command line, modify proc command line in transit to remove the SE Linux checks and make it permissive throughout. Init also executes a large number of .rc scripts, which are the init scripts for hardware and services. Because I'd restarted this whole process, these RC scripts were being executed a second time after they'd been done on recovery. Unfortunately, reinitializing some hardware components a second time in Linux causes kernel panics because it doesn't know what to do with the process. It doesn't know what's going on. Luckily, this could be avoided just by taking that same ptrace read override and making any hardware initializations just have an empty file there instead of a long, complex file with all the configuration and service installations. Also, once this process had completed, there would be a lot of services that would still be running in the recovery context rather than the Android context. So there would be things like QTE, the TE, etc., running in the wrong recovery context. This would prevent things like pin unlocking from working and getting access to the rest of the device. But this could trivially be resolved by killing the processes before the newer version of init started. The system partition of the Android OS uses dmverity for mounting things like the system partition, which needs to be read-only and not modified, but is also still an ext4 operating system. Because I wanted to modify the system files, I decided to find a way to override them temporarily on boot. What I did was use the mount -- bind command, which allows you to override one file with another, essentially, temporarily, which allowed me to disable all the system services, things like root detection and security, and replace some core apps and frameworks so I had really granular but temporary control over the device that would be removed after I rebooted. So we're going to do a quick demo now of this whole process. I will warn you, is slightly abridged, otherwise we'd be standing here for 5 minutes as we watch a phone boot. But there's me executing the command. It then tries to perform an OTA update. And then you'll see the screen go off when all the recovery services, etc., have been killed, and the Android process is restarting. So now Android is started up from the recovery instance without ever having to reboot. And at this point, I found that I had to restart the screen to get the touchscreen to work again. But after I did so, I could go into phone, go into ConnectBot, and at this point, I had added a telnet backdoor into the device with full root access. So I had a very interesting observation from this, which I was really quite excited about, was the fact that when I booted into Android, the recovery file system and context was still there and still accessible. So for debugging purposes, I'd added a telnet server into that so I could see what was going on. And I found it was still running at this point. So there was an entire file system that Android had no idea about and really couldn't do much with. The only difference was that switch root had deleted a lot of the files within the file system because they weren't necessary anymore and it was trying to save space. But these could be repopulated just using BusyBox again. The recovery RAM disk was hidden from Android entirely, but the recovery RAM disk could still access Android by going through proc1 root, which is taking you to the root file system for process 1. This meant that I could log into the recovery context, mess with Android, but Android really didn't have much idea about it, apart from maybe seeing processes it didn't quite understand. I decided to expand this and add a whole Debian root file system into the device and use the same idea to give me very granular control over what was happening in Android without Android really having an idea of what I was doing. Root access via this method was found to work consistently, so the tool manipulating init ran constantly throughout this and stayed connected to init non-stop because it was required for a lot of the different interaction that was going on. But I found that I never had a crash from this, there were no real problems, and I could leave the phone on for days without any issues. But also, I could just reboot the phone if I wanted to and have no ill effects, and it would reboot with no root access whatsoever, no NCLDNOX disabling or anything, and it could be used as a standard phone again, with the phone having no idea about the fact that it had been manipulated in this way, which was quite exciting. Now we're going to on the slightly more technical one, which is going to be exploiting the secondary bootloader in an Exynos-based phone. So Exynos-based devices have had significant research placed on them on their download mode, which is their Samsung's proprietary protocol for deploying new OTA update or new updates of the thing or recovering them from irreversible errors. This all focused on the high-level download protocol, however, and not on the USB stack underneath. And I really wanted to see if I could find a vulnerability in the core USB stack, because in there I would not only have a vulnerability in their download mode, but also their fast boot mode, which is used for other administration. So the target device in this instance was the Samsung Galaxy A04s, released in August 2022, which used the Exynos 850 chipset, which is also a fairly recent chipset, but it's not a high-end one compared to the latest and greatest Samsung phones. The secondary bootloader in Samsung is called S-Boot, which has multiple different modes and features. The first being standard boot, which just takes it up to the high-level Android operating system. Download mode, which was already mentioned, fast boot mode, and then upload mode, which is a mode which is used for administrating the device when it's in a very, very broken state, essentially. This is all encompassed in a single firmware binary called sboot.bin stored in the file system. But if I'd found a vulnerability in the USB protocol, I would have a vulnerability in all three of the sections, so download, fast boot, and upload. So the core part of the USB stack is USB control transfers, which are in every USB device. And they use some standard parameters, which are BM request type, B request, W value, W index, a buffer, and then a buffer size, which is a 16-bit value. It's very basic, but it's also the core component of how USB works for Samsung, for all USB devices. Additionally, fuzzing control transfers is very, very simple. Because control transfers are not usually part of the core protocols being used by a device, they can just be randomly attacked using just rand in every single parameter, including the buffer, and seeing what happens. Unsuccessful requests will usually be rejected by the device that you're targeting, giving you a really, really granular control over knowing which requests are doing something and which aren't. As you can see there, I have a function call, which is the basis of the fuzzer, which got me to a full secure boot bypass. And as you can see, it's not very complex. So initial fuzzing attempts with this, sending purely random data and purely random parameters, caused the device to reboot into a failure mode, which said that the update that was being performed had failed completely. This occurred when an OXF6 value was sent as the B request parameter, which didn't really mean much to me, but I tried this a few times and saw the same thing. Luckily, I could get out of this failure mode by using a command line tool called Heimdall, which is used for updating via this download protocol, which allowed it to reboot back into the standard Android mode without any issues. So I continued fuzzing, filtering out the OXF6 command because I didn't want to keep soft bricking my phone. And I found one that would crash the phone and cause it to reboot back into the operating system in Android. This was born from a single seed, which was then just repeated over and over again to make sure that it did the same thing every time. And I cut out transfers in the sequence that was being performed until I found what the root cause was. One transfer was sending a get descriptor request, but sending in the wrong direction, transmitting data instead of receiving it. And the second was a valid get descriptor request, which was receiving the get descriptor stuff and then causing it to crash. So we come on to probably the biggest vulnerability you'll ever see on a USB device ever, because it is at the control transfer level. And this is descriptor overwrites. So control transfers have things like get descriptor, set address, etc., which have very specific directions for the data. And get descriptor is only ever meant to receive back to the host. This includes information about the device itself, like its vendor ID, its product ID, some string data, and that sort of thing, as well as a length that is stored as the first byte of the data so that you can read a little bit of the descriptor, see how big it's going to be, and then create, spread out your buffer as needed. If you can overwrite this, you can overwrite the first byte of it and give yourself expanded access to the memory within the chip. So instead of just having the descriptor, you can see all the memory next to it. Which usually includes pointers to other descriptors. So if you can overwrite them, you can overwrite where the memory is for other descriptors, which means that you'll have an arbitrary memory read-write within the device. So what's interesting to me is that most USB stacks don't actually check this control transfer direction appropriately. Essentially, you're meant to check with an if statement whether the direction is correct on the transfer that's being sent to you. So if it's a get descriptor request, you should definitely be checking if it's actually trying to receive data and trying to send it. What I found, though, is that in most targets, rather than them checking it explicitly, their hardware is explicitly going for sends and receives rather than being agnostic in that sense. For instance, in this example from the STM32 USB-D stack, which is quite well written and easy to understand, it has the request for receiving a device descriptor, and then there's no checks for the direction. However, it sends a send data request within its hardware rather than just doing a transfer request of any kind. In this case, however, on the Exynos device, it wasn't checking what the direction was that was going on. So what I wanted to do was overwrite that first byte, which was the size byte, and then give me a full view of the memory adjacent to the descriptor within memory. This was ineffective, however, and it seems that the data size was actually being stored in a separate parameter somewhere within the bootloader. Luckily for me, however, there was just a buffer overflow within this anyway, so I could overwrite all of the data next to the descriptor just as I wanted to because there were no checks on the size against it. Because of this, I could then start brute forcing memory to find out what data was next to it. Rather than having it directly, I would have to find out for myself. So I found the size of a buffer that would cause the device to crash in the same way, and then I would change that final byte, and I would increment it by 1. And until I found a byte that was accurate, that was the same as what was already in memory, the device would keep rebooting and keep rebooting. But if I hit one that allowed the device to continue working, it can move on to the next byte and do the same thing until it built up a big list of pointers, which were pointers to other things within the USB stack. So as you can see, there's F941AO E0, which is a pointer to another descriptor. Being able to modify these pointers and then read and write the other descriptors they were pointing to meant that I had full access to the entire memory of EL1 without ever having to perform any other form of exploitation. I could read and write any memory on the chip as long as it was within the context of the secondary bootloader. I used this to jump memory. So in the device, I saw that most of the memory pointers I was looking at between F9 and 6 zeros and FA and 6 zeros. So I decided to create a memory dumper just a bit before that, assuming that before that would be the actual code for the secondary bootloader. And I was correct, finding that the secondary bootloader code started at F88 and 5 zeros, followed by the RAM contents, and then the frame buffer, which was at FA and 6 zeros. And I wrote just a nice little program that would just dump that memory. What was interesting is, if I wanted to, I could also use this for a cold boot attack. This is an attack where you reboot a phone and then dump the memory that hasn't been cleaned off from the reboot, giving you access to the data on the device without ever having to do a pin bypass and that sort of thing. I was a bit concerned about exploiting this further because most devices nowadays use DEP, which is data execution prevention, meaning you can't overwrite code that is going to be run. So as the bootloader was running in RAM, I thought they maybe hadn't configured it properly, but they had, meaning that I couldn't overwrite the running secondary bootloader because the phone would just hang saying you don't have access to that memory, the MMU's blocked you. However, if I tried to execute code within unused sections of RAM, which just hadn't been allocated at all, I had full read-write access and full execution access, meaning I could write any code I wanted to into it and do whatever I wanted. What I wanted to do is patch in some new functionality. Essentially, what I wanted to do was use this to get myself into a position where I could modify the kernel within memory and then start that kernel, giving me access to the device, bypassing NOx protections and that sort of thing. So I like to do these things in C. So I write my code in C and then use GCC static no standard lib, meaning that it will just give you a raw subroutines compiled out, which you can then use object copy to then turn into binaries that then can be dumped into memory with this exploit. I wanted to use fast boot mode for this because fast boot uses string-based commands, which are usually stored within a table within RAM. One pointer points to the function name, and the other pointer points to the function itself. This will allow me to essentially run a command, execute the code, see what happened, and then run it again and do quite a lot more debugging than I'd have usually. And I just chose the get variable command for this because I only had to get variable and reboot in the fast boot instance, and I didn't want to keep rebooting the phone by accident. So the table usually looks like this. So you have the string, reboot, then the reboot function call, and then get var, and then the get var function call. So very simple and very easy to modify if needed. What I wanted to do, as I said, was re-implement boot. So this would allow me to modify the kernel after it had been verified by all of the lower level systems, meaning that things like signature verification have been completed, abstraction had been completed, and that sort of thing. And if I could modify it after this had been done, I could do whatever I wanted to the kernel, the file system, whatever, root it if I wanted to without hitting NOx, hopefully. What I found, however, was that no USB-based mode on the device had a way to just start booting the phone. Usually fast boot, which is the protocol we were using on other devices, allows you to boot from memory in certain instances. However, in this instance, there was no capability for that. And calling into the standard boot functions that were used by the standard boot mode just caused the device to hang for reasons unknown to me. There were two options for me re-implementing boot. The first thing I could do was copy the entirety of the running memory into a section of memory where DEP hadn't been enabled, so I could just rewrite it as I wanted to and do whatever I wanted. Or I could re-implement the boot functionality from scratch. I decided to go for the latter because there wasn't really enough memory available for me to reboot or to overwrite as much memory as I really needed to perform that. So functions in the bootloader could be just trivially addressed by absolute addresses, and I would just literally point to them and then execute them, point to them and then execute them, knowing what the parameters were, and sometimes modifying things like whether it wanted to perform certain checks. And I could also check if those functions were absolutely necessary for the boot process or if they were superfluous. I could also debug this quite nicely because I had a full memory dump of a successful kernel boot, and I could literally take this and then compare it against a failed boot and see wherever a printf, there were loads of printfs within the bootloader, and just see which ones were incorrect in different ways and which functions weren't working correctly, which was really nice, meaning I could do a one-to-one comparison until I got to the point where the thing was booting. At the end of the whole process, I would directly call into the kernel and then execute it, which included KASLR, which meant the kernel base address wasn't always in the same place. Luckily, the pointer to it was stored statically within memory, so I could just get that pointer and then start executing, which was very nice. After patching in, however, all of the appropriate functions, the kernel was loaded into memory and could be executed. However, it hung and never started Android with the boot logo just staying there completely, nothing happening, no interaction whatsoever, and causing me to have to reboot the phone by hand. However, I decided that if I could debug the secondary bootloader, I could debug the kernel in the same way. So I would take the kernel, and by patching out and knocking out different function calls, I would see what was causing the hang and get my way all the way back to seeing what was happening. So I found that the device froze after the kernel reinitialized the MMU. So usually on kernel boot, it will take a lot of the ARM system control registers and modify them so that they match the high-level OS instead of the secondary bootloader. Because it was hanging at this point, it implied that there was things still going on the bootloader that I didn't know about that were causing code to try to be executed in memory that was no longer accessible to it. So the most likely reason for this was that the bootloader was using threads of some kind, which is very unusual for a bootloader. So most Android bootloaders just use a single thread for their functionality and then sometimes use interrupts for things like the USB communication. But I found that SBoot was found using an RTOS of some kind, which was facilitating multiple threads within the device, which were still running even though I had code execution into one of them, as I found out. And as the kernel altered the MMU page tables, they were attempting to execute memory that was no longer mapped and no longer accessible. So 3 threads were identified on the device. There was the background tasks, which are things like just checking the status, updating the screen, and that sort of thing. There were the USB control transfers, which was what I was messing with, and the high-level USB communication, which was the fast boot communication and the download communication. Each one of these was constantly running, and I didn't really have a trivial way to just pause them or stop them executing, so I wanted to do something very lazy. The simplest solution for disabling all threads would be to throw an exception. This would cause the device to want to go into that exception, do whatever was needed, and then if it needs to return from it, the threads could continue again. However, if I put my boot code into an exception, then the kernel would boot without the threads ever being able to restart again, and the device could start up and just continue working. And recovering from the exception would never be required. So I could just dump the whole bootstrapping code I'd put up in at this point into a vector base address register table and be fine, and it should execute. Oh, sorry. So in ARM64, exceptions are stored in vbar EL. Now, because we're in exception level 1, it was EL1. And it points to a vector address base register table, which includes functions which all are at maximum 128 bytes long for each exception. What I decided to do is not try and work out what exception was what, and just have a NOP sled throughout all of the exceptions down to my boot code, which would then execute if any exception was called. I found that this would actually let the kernel boot, meaning that I got slightly further, but found that it would revert to recovery mode halfway through and tell me that there was a problem mounting the file systems. This error message, fs manager mount all, suggested that it wasn't being able to decrypt the user data partition, which is encrypted by default, meaning that probably some of the more security-conscious components weren't being enabled correctly. What I found was, looking at my logs, that key storage and tgris, which are 2 components of the boot process, were being called twice, once by the standard boot functionality and once by me during my exploit. This second initialization was causing the rest of the state machine of these particular components to fail, meaning I'd need to stop myself executing them twice. Luckily, this could be done just by re-implementing the function that was calling them completely and just knopping out those sections, which was very simple and meant that the device could then get fully all the way from the bootloader all the way to a high-level OS Android. So we're going to do a demo now. So as you can see, we're starting in fast boot mode at this point. And immediately, it will switch to the boot screen and then to the Samsung Galaxy screen saying secured by Knox. At this point, you may see a tiny flicker, which is when it's switching from the bootloader to the kernel, which is still wanting to use that image. And at this point, it was still possible that the device would potentially reboot into recovery mode and say it failed if I had messed something up in this process. However, because the Knox message disappeared, it meant that we're now into the Android file system, and it was starting the services, it was starting things like loading the root file system, making sure that it could connect to the internet, making sure there were no other boot level checks it was checking. And in a few seconds, hopefully, you will see it then boot into my custom kernel, which won't be very interesting, but will show that we could boot into Android from fast boot mode. Because I really want to mess with the kernel more than anything else, because I'd been modifying it in such a granular embedded OS way from the bootloader, I decided to keep it very simple for my demonstration today and just show the word hacked within the version string of the kernel. However, because I could rewrite any part of the kernel, and as long as I was careful, I could modify any component I wanted and hopefully not trigger Nox. Now, it was still likely that I would at some point if I got a bit too laissez-faire with things, but during this whole process, I modified things like SE-Linux checks slightly and haven't yet triggered Nox, which was very nice. So there's some final notes on this. As the exploit can now be triggered using an exception, any boot mode, so download, fastboot, etc., could be used. I could re-implement this for download mode. I could re-implement it in any way I wanted, and it should boot consistently. This meant that even vulnerable Samsung devices without fastboot mode could be exploited in the same way, because fastboot mode is only used on some of them. There was always going to be a risk of triggering Nox with this, but at this point, I hadn't seen it. The initial vulnerabilities were disclosed to Samsung in December of 2022, and Samsung provided constant updates on progress and queried things when they needed to, and patched the finding within 3 months, which was extremely good of them for something that was so pervasive. The target device was updated and found to no longer be vulnerable to the Descriptor overwrite vulnerability, so there was no code execution there anymore. I'll be releasing tools for this, which you'll be able to see soon. In conclusion, most devices will still have simply exploitable vulnerabilities despite the resources used to mitigate against them. And even with basic vulnerabilities, the effort required to go from a proof of concept to a full exploit can be extremely rewarding. And lastly, even on targets which have had a huge amount of research performed on them, there will still be a vector that no one else has tried. Thank you very much.